Hi, I'm Alistair, and this is a video about creating special effects using PDLC film. So this is a PDLC sheet. You can see it's a thin, flexible sheet, and by default it has a kind of a milky, white, opaque appearance. It lets sunlight through, but you can't see through it. But if I apply a voltage across the sheet, it turns completely transparent. And I'd say this is underused as a creative effect. It can create pretty magical interactions because it toggles between opaque and clear almost instantly, silently and with no moving parts. If you hear a click on the video, that's just the noise of me activating this switch here, which supplies power across the sheet. And unlike some visual effects like a video display monitor, it doesn't feel like a digital electronic component. It's just a surface, like a piece of paper, which means it's easier to integrate into lots of different themes which don't need to feel high-tech. Here I've made a window frame in which each of the 12 panels is a separate piece of PDLC film. And then I've got a keypad which toggles relays that energise each of the panels individually. So in terms of specific interactions that could use a prop like this, in an escape room you could use it to reveal a mechanism behind the panels, such as the layout of a maze or some other physical interaction which requires players to reveal in sections and to be able to see what they're doing. Or you can have a memory matching game where you activate panels to reveal objects or symbols behind them. If you reveal panels that have a pair of matching objects, then they stay revealed. Otherwise they become opaque again and you have to try to find a different pair. Or you could use a PDLC panel between two rooms or areas and have players on either side of the panel that have to share visual information, but they can only do so when the panel is clear. Or some kind of look and remember memory recall task where the sheet reveals something in a different physical location from the place in which that information needs to be input, and players need to remember what they saw on the other side before it's covered up again. And that could be combined with a timing or a coordination challenge. So the button to reveal the sheet is not placed immediately next to it, but somewhere else. And either you have a momentary reveal that only stays visible for as long as the input is held, or perhaps only lasts for a limited duration from the moment the button was pressed before the film becomes opaque again. So lots and lots of potential uses. It's not particularly expensive or difficult to use, so let me give you some more information about the hardware setup I'm using here. So I'm going to start by showing you a closer look at one of these sheets. And I'm holding it down in front of the bench now because unfortunately the lighting here in my workshop makes it tricky to demonstrate some objects on camera. In that last scene you'll have noticed a lot of reflections from the light shining off the surface of the panels in the window. So I'm hoping that if I show you here at a different angle and different environment, you'll be able to see the contrast a lot clearer between when the panel is on or off. So first of all, I want to talk about the opacity through the sheet when it's off. So if I'm just going to lay out some cards on the table first of all, and then if I rest the film directly on top of those cards, you'll be able to see that you can clearly see the details through it. Even when the film is completely unpowered as it is now, you can see all of those cards. Now, the way the film works is that it has a load of crystals that are suspended in a polymer. And by default, those crystals are all jumbled up in random orientations, which causes light to diffract in random directions as it passes through the sheet. But when an object is pressed right up against the film, there's not sufficient distance for that diffraction to have any effect. Now, as I move the sheet away from the object behind it and increase the distance that separates them, you can see the details of the card become less and less distinct as the light becomes more and more diffused. And you can use this to create a kind of a pretty neat effect, depending on whether you want players to have an indication of what might be behind the sheet before it's revealed or not. You can place it, so this is a distance of about 1 centimetre away, and you can kind of see a blurry outline, but you can't see the details there. If I get much further away, you can't make out that there's any object there at all. And you can have different effects. So if I put my hand there, you kind of get effect a little bit like you might have seen in sort of horror movie posters, where you get this blurry, indistinct outline of an object. So you can kind of play around with that depending on what kind of effect you want before the reveal. Now, when it comes to activating the film, you simply need to provide a voltage across the two sides of the panel. So you'll see I've got a contact here, which is attached to this red wire, and on the opposite side of the sheet, I've got a contact here with a black wire. And that's all there is to do. There's no other circuitry or chips or anything else involved at all. It's just a sheet with two contacts, and you need to provide an AC voltage across those contacts. Now, the sheet doesn't consume very much power. It's normally about 3 watts per square meter. So an A4 sheet like this is about 1/16 of that, so it's going to use about 0.2 watts of power, very little indeed. And that means you can power them from batteries. Here I've got a smaller sheet, and it comes with this little power bank here, which takes 2 AA batteries. And I need to convert the DC power supply into an AC wave, and that's what is happening in this little unit here. So these often come supplied with these, and inside one of those what you'd find is a very simple transformer circuit like this that just takes the DC output from the batteries and converts them into an AC square wave that activates the film. Now, if you want to use a bigger sheet like this one that I've got here, you'll need more current, so you'll probably want to use a mains adapter instead. This is the one I'm using, which has 240 volt input and 60 volt AC output. And if I plug that in, you'll see that it instantly turns this sheet completely transparent. And then I've just put an inline switch in the wire here, which is what I was using in the video. So let me show you how I implemented that in my window panel prop, which I demonstrated earlier. So this is just the reverse side of that panel. You can see I've got my 3x4 array of PDLC film, and those are being controlled by these 12 relays at the bottom here. So I've got an AC power supply coming in, and then these relay modules are directing that AC current to the PDLC films individually. So remember, a relay is just a mechanical switch. It's a metal contact that closes between a common terminal and either a normally closed or normally open output. So that means you can use it to switch AC power just as easily as with DC power. So long as you don't exceed the ratings on the relay module, that's absolutely fine. And like I said, these actually draw very low power. Now, the relay modules themselves, they're being controlled by the ESP32 microcontroller over here, and that's also what's listening to the button inputs from the keypad. Now, this is a 3x4 matrix keypad, so that's got 12 inputs in an array, and we've also got 12 outputs in the relay module. So if I was to assign each of these to an individual GPIO pin on the ESP32, that would be an awful lot of inputs used up. So instead of wiring them directly, I've actually got 3 PCF8574 port expanders here. And these are I2C port expanders. So I connect them to the ESP32 just using 2 GPIO pins, one data and one clock line. And then I can interrogate those to receive the inputs from the keypad, and also to control all 12 of the output channels of the relay modules that then energize the PDLC films. And here's a fritzing diagram of that same wiring, just to make it a little bit clearer. So I've got my AC power supply here, and you'll see that one of the terminals of the AC power supply is shared between one of the contacts on all of the sheets. That's this black line here. Then they have the other contact from each sheet going to the common terminal of a unique relay. So one relay per sheet, that's why I've got 12 sheets and 12 relay modules here. and that goes to the common terminal, then to the normally open terminal of every relay. Well, I've got those daisy chained together going to the other terminal of the AC power supply. So what that means is that when this relay is in its default state, the common terminal is connected to normally closed. This is a broken connection here, and no power is going to be supplied to the PDLC sheet. When the relay is energized by a signal from the ESP32, the contact is going to move across internally to connect the common terminal to the normally open terminal. And that's this long daisy chain string. So however many relays are activated, each one will have its common terminal wired into this circuit here. That is going to form a continuous circuit to the corresponding panel, and that's what's going to cause it to become transparent. Now, the relay terminals themselves have a signal line for each of the 4 channels, and they are controlled by the outputs of these PCF8574 port expanders. So I've daisy chained again 3 of these together. These are great little boards if you're not familiar with them at all. It's a very useful way to expand your inputs and outputs for any microcontroller project because they have 8 pins on each one, and you can literally plug them into each other to expand more and more, and you only need to connect a data and a clock line at the end, which I'm using GPIO 22 and 21, which are the default I2C ports on the ESP32. I'm also supplying them with power, and then the relay modules themselves, well, these are 5-volt relay modules, so I'm supplying them with VCC of 5 volts and a ground, which is also what's powering my ESP32 here. Now my keypad, well, that I'm also reading the inputs from a PCF8574. I've actually got 4 unused channels here, which I could have used, but I've decided to move those onto a new module here. There's no particular reason to. I could have used 4 of these and then the next 3 of the next module along, but I just thought it makes it a little bit tidier to maintain it like that. Now I should mention that 60 volts is a higher voltage than most projects I make on this channel, which are more commonly low voltage 5, 12 or 25 volt DC. And that does mean you need to exercise more caution to ensure that it is safe. Now current limited high voltage in itself is not dangerous. Static electricity is a good example, which can be measured in kilovolts but has very little current. If you had 1 meter square of PDLC film, that would only draw about 0.05 amps of continuous current, or 50 milliamps. And as long as you're using a properly current limited power supply to that film, that should be perfectly safe. But nevertheless, you should ensure that your wiring is secure, that players don't handle exposed contacts or any other part of the circuit, and that you use an appropriately rated power supply. And just for the sake of completeness, I'll show you the code that's running on the ESP32, but to be honest, the vast majority of this is just incredibly generic code to read inputs and outputs. So I'm including the wire library, which creates an I2C connection to the PCF8574 expanders, and I'm using 3 different modules, so they all need to be assigned a unique I2C address. Now there's 3 little jumpers on those PCF8574 modules, and depending on where you place the jumpers, you can choose from a different address. The default address is 020 in hex, and I've got 21 and 22. So you just need to move the jumpers to the correct position on the board, and then add the corresponding address in the code here. They don't have to be sequential at all, but you'll probably find it easier if they are. Then I'm defining a keypad, which is going to be my input, but obviously you could adapt this code to use any kind of input you want. You could have an MQTT message, a Bluetooth message, a simple button. This is just, for the sake of showing you the way I'm using it. Here I've got a single byte value, which represents the input and output state of each of the modules. So those 8 channels which we can output to control the relays, and the 8 channels of input which we can receive from each of these 3 modules at the I2C address here, those are written as a single byte value. So all 8 bits we're going to read from the keypad, and all 8 bits we're going to write to the relay outputs in a single go. So this is just the default value, and we're going to use bit masking to set the individual bits of that value in a moment. This is the layout of my keypad. This just means I can refer to the values in code. I mean, I just used a keypad that I had lying around, which follows a basic phone keypad layout, but obviously you could put symbols here or any other input you want really. All this here these are just some global variables to handle some debouncing of the input, so I don't accidentally hold a button down and toggle the PDLC film on and off very quickly. This function here, this is a custom mapping, because effectively I realized after having wired everything up that I'd wired the panels to the relay modules in a different orientation to the way that I'd wired the keypad inputs. So rather than pull everything out and rewire it again, I just thought that's easier to adapt in code. So this simply says when I press the button that is located at the 3 position, so the top right hand corner of the keypad up here, I want to activate the 7th relay channel, because that is the one that the common terminal was wired to the panel that was in this position. If I press the key that corresponds to the keypad location of the number 6, the one immediately under it, you can see I wired that to relay module output 6, then 5, then 4. So going down the right hand side of the keypad, I'm going down the relay module 7654. Then when I go to 1, which is on the left hand side of the keypad, well, that maps to relay channel 11, 10, 9, 8, and then the central column is 3, 2, 1, and finally 0. So that's just a very simple way to show you how you can remap in software, rather than if you ever plug all your wires in and you find out, oh, no, I've done them left to right backwards because I was looking at it from the front or the back or whatever. I've just remapped that in code. I'm just using very simple, so this is the inbuilt Arduino wire library. So this just enables me to write that byte value to a given address. That's going to control the outputs, and the read PCF is going to request a single byte from the corresponding address. So we'll pass in the address of the 2 modules that are controlling our 2 sets of relay outputs here, and we will read in a byte from the keypad, so from that address. And then we will toggle an output. So this toggles a single bit value in that PCF state byte that I declared as a global variable at the top. And depending on which relay channel we want to toggle on or off, we set the corresponding bit in the PCF state byte value before we then write it out to the module. I'm actually splitting it across 2 banks of 4 relay modules, so I have to work out which bank it is that I'm writing to first of all, whether it's this one or that one, and then I set the bit value in the corresponding byte to send to that output. When I want to read the input, well, that's rather similar. So I'm using the read PCF command. I write a high value to it first, and then I read to detect which combination of row and column pins have been joined together. That's what happens when you press a key on the matrix keypad. You've got 3 columns and you've got 4 row pins, and at every intersection between them, when you press that key on the keypad, it's going to short those 2 together, and that's how we know what key has been pressed. So we loop over all of the columns and all of the rows, and we work out which one has been pressed, and then we return the corresponding key that we defined up here. So if the middle column and the bottom row have been shorted together, we know that the key that we're calling 0 has been pressed, and then that gets passed into here to say, okay, in that case we're going to activate relay channel 0. That's what's going on there. And I added a debounce function to that. So this is the kind of the raw input. This just reads the value directly from the input from the I2C interface, but we actually want to get a little bit of debouncing on that to make sure, like I say, we don't accidentally toggle on and off the film too quickly. So this is where I just define a very, very simple debounce function. I define a debounce and a release time in milliseconds at the top of the code here. And only when the input has been changed for greater amount of time than that, that's when we change the value, or that's when we read a different value rather, and we say that a new button has been pressed. That just stops us toggling too quickly. And all of that gets called very simply the setup function. We just initialize the I2 interface. We write the initial values to the two relay modules, to the two sets of 4-channel relay modules. Then we say we're ready. And then in the loop, what we do is we check our input. So we check the debounced input, and that in turn called the raw input up here, but it only changes it when that has changed for the sufficient amount of time that we specified. If we have received a key from our input and that key has not already been handled so far this frame, that's when we change the bit in the corresponding byte of output. So whether it's in the first bank of 4 relays or the second bank of 4 relays, we update the byte value for that, and then we toggle the corresponding output from the relay. So that's just the code which I wrote, but really this is just an example. You can modify the logic however you want. All you need to do is to trigger the relay module which controls the power supplied to the PDLC film, and you can use that based on an input or a sensor or some control signal sent by your control software, however you want to implement that logic. So that brings me to the end of this video about PDLC film. I hope it's given you some ideas or inspiration for ways you can use this, in my opinion, underused material in novel and creative ways. And if you do end up using it, please do let me know in the comments below. I always love to hear about some of the creative, amazing, inspiring projects that people out there are coming up with. So I do really want to hear from you if you do use it. If you'd like to download the resources that accompany this project or any of the other tutorials in this channel, you can find those over on my Patreon account. So the wiring diagram, the links to any resources I used, the code on the ESP32. And if you are a Patreon supporter already, I just want to say thank you so much for your support that enables me to create these videos each month. I really do appreciate it. So thank you. Otherwise, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.